So in this video, we will talk about inferences about B1. So just for an information, recall we assume epsilon xi are normally distributed. Hence, yi's, which are equal to beta 0 plus beta 1 xi plus epsilon I, are normally distributed as well. And remember, we said that we don't know sigma B1 or sigma square B1. So it was equal to sigma square divided by sxx. We don't know sigma square, hence we cannot make any inference about B1, but instead of sigma square, we can just use an estimate of S square, which was SSE divided by n minus 2. And using this, we can just write this, S of B1 squared, that's equal to S squared divided by Sxx, and this is S of B0 squared. Okay. So using this, we can just make inferences on beta 1 and beta 2. So it turns out that, remember, so this is B1. B1 was normally distributed minus its expected value, which is beta 1. Recall that we said B1 was an unbiased estimator of beta 1, divided by its standard deviation, which was just take the square root of this. Just take the square root of this, s divided by root sxx. Well, it is a t-distribution with n minus 2 degrees of freedom. Okay, so that's great. We can just use this in order to make confidence intervals and hypothesis tests. Okay, confidence intervals and hypothesis tests. And it turns out that, well, a confidence interval, 100 times 1 minus alpha percent confidence interval, is given by this equation, right? Remember, it was mu x bar plus t alpha, let's say x. So this is an element of, let's me just write x bar plus minus t alpha times s of x bar, which was s of x bar, it was s divided by root n, right? We have exactly the same thing here. Instead of x bar, I have b1, t, so this is t alpha, sorry, t alpha, they are the same. Instead of s of x bar, I have what? This is s of b1. Okay, completely the same thing. Now let's make an example. So assume we have a GPA and ALES scores of 33 students in terms of percent ranking. Okay, so X denotes the percent ranking of the students in terms of their GPA, and Y denotes the ranking, the percent ranking of the students in terms of the ALES score. Okay, so for example, just look at this one. So this is the first guy. His GPA is in the third percent. Okay, 3% of the whole students in, let's say, I don't know, in the engineering faculty, and it turns out that, well, his ALES score is in the 5% of overall engineering students in the exam. Or let's look at here. There's a guy here whose GPA is at 32%, and his ALES score is at 32% as well. Or there's another guy here, let's look at this one. His or her GPA was 33%, 43%, and it turns out that, well, his ALES score or her ALES score is 37%. You see, for example, here you have two guys, and their GPA scores were the same, but this guy has a 34% in ALES, and this guy has a 32% in ALES. And what we will do is, remember, we have 4 steps. The first step is just find B0 and B1. Okay? And the second step is, remember, just check your assumptions, but it was later in the multiple linear regression phase. Check assumptions. Okay? And the third one is, we will just try to make inferences on what? Beta 0 and beta 1. Okay. So just using the formulas that we have given in the previous slides, it turns out that, well, B1 is 0.90 and B0 is equal to 3.83. So what does this mean? Let me see that. Okay. So this means y hat is equal to 3.83 plus 0.90 times x. Okay, so this is the predicted value. Okay, so this is the predicted regression line of what? Of this mu y given xi equal to beta 0 plus beta 1 times x. So this is my b0. This is an estimate for what? Beta 0. And this is my b1, which is the estimate for beta 1. Okay. So for example, if you are in 10% okay, in your GPA, then just put this into this formula. Then the estimator, the estimator that you will find is y hat is equal to 2.83 plus 0.90, right? Times 10%. So I will just write it like this because that's the 10%. That's how we just construct this regression. So 10 times 0.90, that's equal to 9. So this is equal to 12.83. Okay, y hat is 12.83%. Okay. So what does this mean? This is, in fact, this is, remember what we said, this is the estimate of mu y given xi. So what is xi here? Xi is equal to 10%. Okay, so in fact, this is the, so remember, this is the x bar of, remember, we have x bar of mu, so this is the x bar of this mu. But again, remember, in linear regression, we have many mu's, okay? So this is the estimator of which mu? This is the estimator of mu where you have xi is equal to 10%. So this is the estimator of the people, of the students whose GPA ranking is 10%. Okay? So what does this mean? This means that on the average, if people from this university, students from this university who has a GPA of 10%, okay, whose ranking is 10% in the GPA, take the ALES exam, then their ALES score will be on the average 12.83%. Okay. But of course, this is an estimate we can just use for any guy. So if a student whose GPA score is 10% takes the exam and asks you, well, what will be my ALES score? Okay, just give me an estimate. Then this is your estimate. Later, we will just give a confidence interval on this estimate and a prediction interval, right? So we will make a confidence interval on mu and prediction interval on a single observation. Okay. So this is the data that we have, remember. So this is the first observation, okay, 3% and 5%. Just go back, you see 3% and 5% here, then 5% and 11%. Oh, sorry, just go back. Sorry, 7% and 11%. So this is 7% and 11%. So this is 7. Sorry, board. Right. This is 11%. And what is this? Is 3. Okay, and this is 5. If you just put all of them, well, this is the true theoretical regression line. This is the true hypothetical regression line that we don't know. Okay, we will never know. And this is the estimated line, which we estimated using this 33 different points. Okay? We estimated using this 33 points. So for example, if you just go and take another sample of, let's say, 33 guys, or even another sample of, let's say, 40 guys, and then you will have a different estimator for B0 and B1. What does it mean? You will have a different estimator for this line. It was the case in our previous examples. So remember what we said. We said X bar of, for example, the stats class will be different than it will be not equal to, let me just write here, X bar of the, let's say, production planning class. Okay, both of them are point estimators of mu of this university, but they will be different. Similarly, if you just pick guys in this class and guys in another class and try to fit a regression line, then you will have a different B0 and B1. Okay, in this, for example, let's say this is stats. It will be not equal to B0 and B1 of the production planning class. Okay, the idea is the same. So the next step is just try to find the 95% confidence interval for beta 1, okay? And, well, we found that, well, the point estimate is 0.904. So remember, B1 is an estimator for beta 1, just like X bar is an estimator for mu. So we will just try to make a, okay. So what was the formula for um, the confidence interval? We will just say beta 1 is an element that's B1 plus minus T alpha over 2, which is 0.025 here, times S of B1, okay? How to calculate S of B1? Remember, if I'm not wrong, S of B1 is equal to S squared divided by SXX, if I'm not wrong, right? So what we need is just try to find S squared first, and what is S squared? It was SSE divided by n minus 2. So we need SSE, and so on and so on. So this was the formula for SSE, okay? So S5I minus B1 times SXY, and so on and so forth. And it turns out that S squared is 10.43. What is this? This is the estimator for sigma squared. And what was sigma squared? Again, remember, we said that epsilons are, okay, let me just erase this part. So we say that, well, epsilons are normally distributed, okay? So remember, we just said epsilons are normally distributed, which means 0 and sigma squared. Well, this is the estimate for this sigma squared. Okay, okay, that's great. Then if you just take the square root of this, S is equal to 3.2295. Okay, okay. Then we will find the S of B1, which is equal to S, right? We found in the previous slide, divided by root square, the square root of SXX. So it turns out that S of B1 is equal to 0.0501, right? Which is almost equal to 0.05. We just plug it there in this formula, then you will have beta 1 is, I am 95% confident that my beta 1 is between 0.80 and 1.01. Okay? So remember, what does this mean? So I have something like this. Y is equal to beta 0 plus beta 1 x plus epsilon, or I have mu y given xi, that's equal to beta 0 plus beta 1 xi. Okay, just write it back as yi xi epsilon I. Okay, so here the beta 1, the uh, the beta 1, the parameter of this regression line, I don't know this, but, well, I am 95% sure that it's between 0.80 and 1.01. So this is the confidence interval for beta 1. So for example, um, um, if you just make a hypothesis test, so remember, we keep saying confidence intervals and hypothesis tests are equivalent to each other. So if you just make a hypothesis test which says that, well, H0 beta is equal to, for example, 1 versus H1 beta is not equal to 1, okay? Using, let's say, of course, at the same alpha level, at alpha is equal to 0.05, then by just looking at this confidence interval, you can say that, well, I can not reject the hypothesis, okay? Not reject H0, okay? Since 1 is in the confidence interval given there, okay? Okay. So this is the, in fact, general way to make a hypothesis test, okay? So you can just use the confidence interval, of course, but in general, how to make a hypothesis test? So just check whether beta 1 is equal to m versus beta 1 is not equal to m. So what we do is we just, this is my test statistic, right? Beta 1 minus m, why m? Because using the null hypothesis, we assume that beta 1 is equal to m divided by s of b1. Again, this is a t-random variable with n minus 2 degrees of freedom. Okay? So, well, here, just make a hypothesis test whether beta 1 is equal to 1 versus now we have a smaller than or equal to part here. Okay, just make this test, beta 1 is smaller than or equal to 1 using alpha 0.05. Well, here we cannot use, right? We cannot use the confidence interval above. Okay, why? Because there the confidence interval is two-sided with same alpha. So this is a single-sided test, hence we cannot use the confidence interval above. Okay? So the test statistic just takes the value, just plug in the values. This is my B1, right? This one just comes from the hypothesis and from H0 divided by S of B1, which is equal to minus 1.92 with how many? 33 degrees of freedom. So this is something like this. I have this. So this is T. This is the T distribution. I have minus 1.92, okay? And to the left of this, what is the area here? It turns out the area is 0.03, okay? So what does this mean? At alpha 0.05 level, this is significant, okay? This statistic is significant. What does it mean? You can reject the hypothesis. And we can just reject H0 and you can conclude that, well, beta 1 is in fact smaller than 1. Okay. So, okay. So an important hypothesis in regression analysis is to check whether beta 1 is equal to 0 or not. So what does it mean checking 0 or not? So remember, mu of y given x equal to beta 0 plus beta 1 xi. So what does it mean beta 1 equal to 0? Beta 1 equal to 0 means that this is 0, which means this is 0, which means, well, mu of y depends on beta 0 only. Or what does it mean? Mu of y does not depend on x, right? So it doesn't change with x. So what does this mean in terms of our, for example, GPA example? Well, the distribution of the ALES or the ALES score does not depend on people's GPA. Okay? You cannot say anything, you cannot make any good prediction by looking at the GPA of people. Or in our very previous example, you cannot say anything about the weight of the people, kilogram of the people, by just looking at their height. So if beta 1 turns out to be 0, it means that you cannot make good predictions by looking at the height of people. Okay, because beta 1 is equal to 0 and you cannot reject this. Okay, so beta 1 is equal to 0 means, well, there is no linear relationship between y and x. Okay, there is no linear relationship. Okay, so how to make this test? Remember, the test statistic was beta b1 minus m. So m is equal to 0, right, from the null hypothesis. So this is equal to b1 divided by s of b1. So, well, it turns out that, well, this is the form of estimate of the slope, which is b1, and then divided by the standard error of test. Okay? So if we just reject H0, which is here beta 1 is equal to 0, we will conclude that there is some, so if we reject H0, we will conclude that there is some linear relationship between y and x. And hence, this model makes some sense. And what does it mean? This model can be used to predict the y values, okay, using the independent variables x. So fail to reject the null hypothesis. If you cannot reject this, if you cannot reject beta 1 equal to 0, it means that there is no linear relationship between y and x. x. Okay, so that's a critical issue. There's no linear relationship. Okay, so what does this mean? It can mean two things. The first thing is there is no relationship between y and x at all. Okay, you have no relationship between them. And the second thing is, well, there is a relationship between y and x, but it's a nonlinear relationship. Okay, so you can just see this in this scatter diagram. So here, there is no relationship between y and x. You see this? As x increases, there is no trend in y. It doesn't increase, it doesn't decrease. There is no change in y in terms of x. Okay? So this is the first case. In the second case, well, as you see, there is a clear relationship between x and y, but it's nonlinear. It's quadratic. Okay. So if you just try to fit a line and try to find b1, b1 turns out to be 0, and you cannot reject the hypothesis which says beta 1 is equal to 0. So it doesn't mean that there is no relationship. It means that there is no linear relationship between between y and x. Okay. So what does it mean rejecting h0? What does it mean rejecting h0? So you just reject h0 and say that, well, beta 1 is not equal to 0 or greater than 0 or smaller than 0. If you just reject h0, when it says that, well, there is a linear term, okay? There is a linear term in the model that relates y and x. It doesn't necessarily imply that the relationship is only linear, okay? There could be higher order relationships, and it can be best seen by looking at again, the scatter diagrams. So if you just reject beta 1 equal to 0, if you just reject this, it means that two things. The first thing is, well, there's a perfect relationship between y and x in terms of linear relationship. So you may have something like this, or you may have beta 0 plus beta 1x plus beta 2 times x squared. So you may have a second order relationship between y and x, where you have a linear relationship between a quadratic and the quadratic linear relationship. Okay? Sorry, a linear relationship and the quadratic relationship. Okay? So as you see here, well, the relationship is something like this, but if you just try to fit a single line to the scatter plot, it will give you something like this. And if you just make a hypothesis that it will say is that beta 1 is not equal to 0. Okay. So you may have something like this or something like